All right, how's everyone feeling today? Good to hear. Happy Monday. Reminder to keep it in your brains. Test 1 will begin in a week. As a reminder, next week you will take it during lab time, either Monday, Tuesday, Wednesday, which again, during lab time means we also have lecture time to review and study. I'm not teaching anything new that week, at least not until Friday. This week, we are covering chapter 7, which will be the last new material before the test, and as with most chapters, it's not going to be a very long one, just direct continuation talking about energy. I plan to wrap that up on or by Friday, which again, we will then swing directly into test review during lecture to make sure everyone's feeling comfortable for it by lab next week. To help with studying for said upcoming test, I will show you that on Brightspace I am constructing a test review tab. First of all, chapter 7 tab, the notes, and then the test review tab below that. It mentions that this test will be on chapters 1 through 7. The tab itself has a list of all the things from that chapter that you need to know for said test. I'll make the list more specific if I find that I need to write anything else out on it. And I'll also be posting things to this tab, including extra practice questions and an answer key for those. I'm also still revising the formula sheet for the class. That's the current draft, bless you, will definitely suffice for the first test. So this is the reversion of the formula sheet currently within the Introductions and Resources tab. So if you haven't run off a formula sheet copy yet, now would be a good time. Again, you can write all over your formula sheet, bring it to the test. The only things you can't write on are the laws of motion and worked out sample questions. But you'll absolutely have access to a formula sheet on the test. If you don't run one off yourself, I will have a stack of them that you can use. And once again, this week, chapter 7, it'll take 2.5 days, and then we will summarize everything before the test is ever administered on Monday afternoon. How do you guys feel? And do you have any questions before we move on today? All right. In that case, let's get started with chapter 7. Again, each week is the direct continuation of the last. We started the semester looking at the laws of motion, motion itself, how force causes motion, and then how motion and force are tied into momentum. And now we will be looking at energy, work, and power. The idea being that in order to exert forces and cause things to move, you must use and expend energy, which is something you've probably noticed before because, man, I can't keep track of all the markers that are dead. Using one of those. That'll do. Every time you exert a force on a mass to cause it to accelerate, you have to use up some of your own precious energy supply. And if you do this enough times, you just tire yourself out and you need a snack or a nap. Sound familiar? All right. What we're studying this week is the connection between your energy use tied to your force expenditure. How energy is used to exert force, connecting it into what we've already been doing. Now, before that, I have a question for you guys. And this is a leading question. It's okay if you don't have a good answer. That's kind of the point of it. Who among you can define energy for me? It is absolutely okay if you can't, because as it turns out, neither can physicists. That was the point. Energy is still very mysterious, even to the scientists who study it, largely because We can't see it. You cannot detect energy directly. You can only detect energy indirectly. If you think you're detecting energy directly, it is still indirectly. Easily one of the first places where humans first noticed the concept of energy was lightning strikes, and still to this day electricity. But when you see electricity, we know energy is moving through electricity. We power the world with it. We know energy travels that way. But the electricity itself, the actual glowing spark, isn't energy. When you see electricity, what you're seeing is plasma, which isn't energy, it's a state of matter. Basically, whenever you see an electric spark, be it a quick static shock or a whole bolt, what's happening is, as energy travels through air, the air gets energized, turns into plasma, and starts glowing. So what you're seeing is light coming off of an object, technically. You are seeing an object, you are not seeing energy. So lightning is not energy. It does carry energy, but the bolt still isn't energy. We only know that the bolt has energy because the plasma is hot and it's glowing. But the bolt isn't the energy. Does that sound all right? Now, very similarly, and this is more a criticism of film and TV, whenever media wants to present something as being energized, they usually just make it glow, which is true. Things do glow when they have energy, but the glowing still isn't the energy itself. Goku possesses energy, but he is not energy. His aura is not made of energy. His aura is made of plasma. So again, the energy itself is still kind of hard. You can't really see the energy itself. You only see what happens when matter has the energy. When air has energy, it turns into plasma and glows. When you have energy, you use it to do stuff. Energy is just this thing that matter can possess that lets it do things. And that is, interestingly enough for my opinion, the definition that physics uses for energy. Something that matter can possess that allows matter to do things. And that's as complex as the definition of energy needs to get for this class. It's this invisible stuff that you can have that lets you do all the things you do. Some of the things that energy lets objects do includes, but is not limited to, move, be hot, and glow. Bless you. And the concepts related to energy we'll be exploring this week include, but are not limited to, different forms of energy, how we use energy, both in terms of machines, but also indirectly about the human body, and how all that ties back to the things we've already been talking about. Questions so far? All right. So, energy is invisible. We always have to measure it through some indirect mean. But through all of those indirect means, we do already know that there are lots of different forms that energy can take. Off the top of your head, what are some types of energy you can think of? Or different places where you know energy must exist, but is in a different state to some other place that the energy exists?
Kinetic energy.
Very good. Very apt of what the next slide is going to be.
Potential energy.
Very good. If something has kinetic energy, it's using it to move. If something has potential energy, it's not using it. It's storing it for later. Any other forms come to mind? Elastic, very good. That's not one that we're actually going to do math for in this course, but it does kind of come up because elastic energy is the type that causes elastic collisions. Remember from Friday when I kept throwing this at the wall? Elastic objects cause elastic collisions because they're able to squash and store energy to then release when they go back to normal. And so when I throw this at wall, no time, the ball squishes, stores all of its energy inside of itself like a spring battery, and then when it kicks off the wall, it releases it again and can kick away at basically the same speed because it stored all that energy for later in the elastic form. So anytime you stretch a spring, you're giving it elastic energy until you let it go. Springs and rubber bands and any sort of thing like that. So yes, elastic is absolutely a form of energy. To list a couple others real quick, thermal is also a form of energy. When you are hot, it is because you have an excess of thermal energy in your body, and to cool off, you have to get rid of it. And let's just put electrical up here, bless you. Oh, one more, chemical. Let's talk about chemical energy real quick. Any energy that's stored in a chemical bond is considered a form of chemical energy, and that's relevant to humans because that's what all your food is. Question? Mechanical. That's a good observation. I'm going to put mechanical up here. Mechanical is absolutely a form of energy, but it's kind of an umbrella term. It's basically a category of energy types. A type of energy is considered mechanical in nature if it relates to physical motion. So, again, consider, if you think of mechanical as a category, kinetic is a type, habit. Try to use a different color for emphasis and it backfires. Kinetic is a form of mechanical energy because kinetic energy has to do with physical motion. If something is physically moving, it needs this type of energy, and this type of energy falls within the mechanical family of energy types. So any sort of physical motion belongs to this branch. Kind of likewise, potential energy is also an umbrella term. Lots of different forms of energy are considered potential if they're stored for later. A very good example of that is most forms of chemical potential energy. Because again, all the food you eat is energy stored within the chemical bonds of the food, which your body, you physically digest the food, you break the chemical bonds, you get the energy out of those bonds, and then you either use it to do stuff or store it for later in a different form. So, all your food is really just chemical batteries. So, lots of different forms that energy can take. We'll talk about a few of them during the semester. For example, we actually do have a couple of units on electricity towards the end of the semester, so that'll come later. Thermal energy will come up occasionally, namely how friction creates thermal energy. But just to quickly mention how that works, when you do this, the force of friction between your palms turns the kinetic energy of your hands into thermal energy in your skin. And again, to cool off, you have to get rid of that thermal energy. So we'll get to this one later. We'll mention this one as it's relevant. The main two types we're going to focus on for the bulk of the course are kinetic and a specific form of potential. So really, a big focus on the mechanical family. So I'm glad that you mentioned that term. Before looking at kinetic energy specifically, a couple more things about energy as a whole. The variable for energy in the math is uppercase E. However, most of your formulas will mention a specific form of energy a lot of the time. And so the energy itself is uppercase E, but there's other forms of it that have more specific variable names. But whatever the form of energy, energy is always a scalar because the carbs you eat don't point anywhere. You know, your body then turns that energy into another form and then exerts force that points somewhere, but the carbs don't point anywhere. Does that make sense? So all forms of energy are scalars, and the unit we are going to be using for energy is joules, spelled Joules, named after a French physicist. Pronounced like the gemstone, but French. Depending on what chemistry classes you might have had, you might be more used to using calories as a unit of energy, and they are both units of energy. It's like the difference between meters and feet, basically. Interesting fact, though, this calorie is not quite the same as the food calories on, you know, your food packaging. If you look at food packaging labels, you might have noticed that the word calorie has an uppercase C on it. That is technically shorthand for a kilocalorie. So one uppercase C calorie is actually 1,000 lowercase c heat calories. And 1 joule is 2.4 of those. So 1 food calorie, bless you, is actually about approximately 4,400 joules. So 1 food calorie, about that many joules, just for context's sake. So 1 joule is actually teeny tiny. 1 joule is not a lot of energy. Just keep that in your brain as a sense of scale. Questions? All right. Now, energy takes a lot of different forms. Let's define 2 of those forms today is what we have time for. The first being kinetic. If the first couple forms of energy humans were consciously aware of included heat and lightning, this was probably the next most obvious one, because anytime you see something moving, that's because it has kinetic energy. For something to move, it must possess kinetic energy in that moment to allow it to do so. And whenever you use your muscles to make something move, you are giving that item kinetic energy. Your muscles get tired because they turn your stored potential energy into kinetic energy to make your body move, and then to give that kinetic energy to other things to make them move. And if you give the energy up, you don't have it, and then you get sore and tired. Again, to compare this back to Newton's second law, when you exert force, you are giving up your own energy. You're exerting that force on matter and giving the kinetic energy to that matter to make its velocity change. So Newton's second law is the mechanism by which kinetic energy is given to things or taken away from them. And the more kinetic energy you have, the faster you move. In keeping with that, to read aloud the formula and to do the whole math as a language thing. Kinetic energy, shortened here to Ke, so again, most forms of energy will be E with something else on the front to tell you what specific form of energy we're looking at. Kinetic energy is equal to 1/2 times an object's mass times its current velocity squared. The V is squared, nothing else is squared. It's only the velocity term. And what this tells us is, any object with mass that is moving must have kinetic energy. If you have mass and are not moving, your kinetic energy level is 0. If you're moving but you don't have mass, you don't have kinetic energy, and that would also make you a photon. That's the only thing that moves that doesn't have mass. But we have mass, and that means in order for us to move, we need kinetic energy. a lot of it, if I'm being honest. All forms of energy we're going to measure in joules. Mass, again, we still want in kilograms. That's every formula I give you. And velocities in meters per second. Formula, how does the formula and the concept feel for right now? Okay. And again, to kind of go back to what I said earlier about we can only detect energy indirectly. You only know something has this if you can see it moving. You can't see the energy itself, you just can measure the motion. Does that make sense? All right. So, since that was a new formula, let's get a couple practice trials for it in your notes. Kind of like with the momentum slides from last week, here I have 3 different scenarios, and each one a object or organism with a different amount of mass is moving at a particular velocity. And I would like you guys, either on your own or working together, to tell me which of these 3 scenarios has the most kinetic energy in it. Formula's here, since it's not on the slide.
You want to tell you the answer?
Yes, cast your vote.
C.
C? All right, we got 1 vote for C. Any other thoughts? Other opinions? Polls closing in 3, 2, 1. B is the winner. C was a very good thought. The issue with both A and C is I gave you the mass in the wrong unit.
I didn't D as what I've got. I didn't do that.
So, to kind of quickly glance at each case, 5,000 gram bowling ball rolling at 3 meters per second. Again, we like kilograms. 5,000 grams is 5 kilograms. So 1/2 times 5 times 3 squared. Again, make sure you're only squaring the velocity. So that'd be the same as 1/2 times 5 times 9 is 22.5 joules. Person walking, 100 kilograms is, human adult. 1 meter per second is a fairly common walking speed. That translates to about 3 miles per hour. And that is 1/2 times 100 times 1 squared, which is only 50. Lastly, the arrow. 100 grams is 0.1 kilograms. Now, this is the fastest one here, and that velocity of 25 meters per second is going to get squared. So this thing moving fast has a big energy requirement. it only just comes in below the walking human. But I want to point out the fairly similar energy level despite a 1,000 times mass difference. The arrow is literally 1,000 times less massive than this person. But by moving 25 times faster, the energy totals are fairly comparable in the grand scheme of things. There's a couple observations I'd like to make about how these examples all interact with each other. First, walking takes energy, and not an insignificant amount. Every moment you keep yourself moving at this speed, you're burning more energy, and yeah, you run out eventually. And then throwing a bowling ball takes half as much as it takes to walk. So yeah, you tire yourself out in a day, even just walking around. Now, as for the arrow, again, I want to point out, since the velocity term is squared, the velocity becomes very important to the way that this math works. If you double something's mass but keep its velocity the same, it needs twice the kinetic energy to remain at that speed. But if you take one object and double its velocity, that's going to quadruple the energy requirement. Just to quickly demonstrate, I'm going to do this calculation again, the person walking, but they're going to walk twice as fast. So 2 squared. 1 squared is 1, so 1 times 100 times 1/2 is 50. But 2 squared is 4. So that puts the energy total at 200 joules. Walking twice as fast takes 4 times the energy. Walking 3 times as fast takes 9 times the energy. The energy expenditure increases exponentially with velocity. This means a few things for humans on Earth. First of all, in my personal opinion, it means running sucks. Because if you go 3 times as fast, you're burning 9 times as much energy as you normally use. And that's why running the same distance as walking tires you out faster. Like, you might get there quicker, but you've got 9 times the energy expenditure. So it's up to you whether that's worth it. This also affects how some of our vehicles function, because the faster you make your vehicle go, the exponentially more energy it needs to get up to and maintain that speed. And that's why actually driving faster drains your gas tank quicker. You might have heard that before. There's a little bit of nuance to that. That's not a 100% rule, and that's because any car that runs on gas has gears. And the way that a gear works is you basically ramp up the energy expenditure until you switch into the higher gear. So every gear switch, the energy expenditure resets. Basically going 90 in gear 5 can be the same as going 10 in gear 1, as long as those are the lowest speeds in those gears. So for maximum efficiency, go at the lowest speed you can in the highest gear. Whether or not that means anything to you depends on how much you like cars in automatic versus manual. What it means for other parts of human existence is this is one reason why we haven't been to Mars yet. Interestingly. Because to get to Mars, you have to go fast. And frankly, you got to go fast just to get to the moon, if I'm being honest. It's why moon trips are super expensive. To get into space, you have to move several times the speed of sound just to, get out of the atmosphere. And then to get anywhere in space, you have to be moving very fast to get there before you die, because things in space are very far apart. So to be going anywhere meaningfully in space, you have to get up to and maintain a speed several times greater than that of sound. And spaceships have a lot of mass, and a lot of mass moving super fast takes all of the energy. Bless you. For a very extreme calculation, You know how in sci-fi, their ships are able to somehow get to another solar system in just, one jump or something like that? In most sci-fi, the ships have some way of going faster than the speed of light. So real quick, I'm going to pop the speed of light into this equation to try to show you how much energy it would take to get a person up to that speed. We're even ignoring the ship, just the requirement to get a person up to this speed. Mass of adult human times 1/2 times speed of light squared. This is 3 with 8 zeros, is the speed of light in meters per second. And I did this calculation earlier. I think it was 4.5 times 10 to the 18th joules. That might be more energy than exists on this planet. That's a bit of an exaggeration, but it's more energy than we can possibly spend on such a thing. And even then, if you could get up to light speed, it would still take you 8 minutes to reach the sun. Still not that fast. Still take you 30 minutes to reach Mars. So don't even trying to find another habitable planet in another solar system. So all that to say, all that to summarize, the velocity is kind of the bigger part of the kinetic energy formula. Going fast costs a lot more energy than going slow. So the tortoise had a point versus the hare. Questions? Okay. I got a couple more factoids to point out before we move on. Namely, I just want to kind of distinguish kinetic energy from momentum because they are kind of frustratingly similar. We spent all last week talking about momentum. Momentum being this invisible thing that matter can possess that causes it to keep moving in a straight line at the same speed. And now kinetic energy is also this invisible thing that matter can possess that compels it to move at a certain speed. You see the similarity? They are similar, admittedly, but they are distinct. Similar but distinct in a couple important ways. Now, admittedly, if you have one, you do have the other simultaneously. And that's evidenced by the formulas. They both have mv in them. And if both m and v are not 0, you will have momentum and kinetic energy at the same time. So they're a package deal. They do come together. Like if you have one, you must have the other simultaneously. You plug the same mass and the same velocity to find the two different numbers. But to start looking at the differences, momentum is a vector. Talked about that last week. And momentum is a vector because when you use velocity to find it, velocity times scalar mass gives you vector momentum. Basically, the momentum inherits the direction of the velocity. If you're going north, your momentum wants you to keep going north, and it takes effort to change that. Interestingly though, kinetic energy, like all forms of energy, is a scalar. It does have velocity in it, and velocity is a vector, but when you square a vector, you kind of just get rid of the direction. It stops being a vector when you square it. Technically, this happens whenever you multiply, at least sometimes, when you multiply a vector by a vector. And velocity squared is a vector times a vector. So that just kind of makes the direction go away. That might seem kind of random, but I feel like it makes the most sense if you were to plug in a negative velocity, and the negative just vanishes, kind of proving that the direction vanished. So kinetic energy is a scalar, momentum's a vector. Momentum wants you to keep moving in the same direction. Kinetic energy just wants you to move. Doesn't care what direction. If you have kinetic energy, your KE is totally content as long as you keep moving in any direction. But the momentum is a vector, so it is more specific. Speaking of momentum being specific, momentum is further different from kinetic energy in that momentum only has the one form it can take. Momentum is momentum. There's nothing else it can possibly be. And that's why last Friday, we talked about how momentum is conserved in a collision. Fair warning, I'm about to throw a basketball at the wall again. In that collision, the momentum of the ball was conserved. The ball, well, technically most of it transfers into the wall, and the wall just doesn't do anything with it. But the momentum was conserved in that interaction because the momentum has no other form it can take. There's no such thing as potential momentum or thermal momentum, it's just momentum. But kinetic energy is just one of many forms of energy. And that means that in certain circumstances, the KE can turn into something else. It's still energy, it's not destroyed, it's just not kinetic anymore. And for that reason, and this is what lab this week is going to be about, that's why I wanted to mention it, where momentum has to be conserved in a collision, because there's no other form it can occupy, kinetic energy is only conserved in elastic collisions. That is, again, this type. Oh, sorry. I'm so sorry. I tried to stop it. That was my bad. Are you okay? Okay. Thank you. Putting that there now. In the elastic type, kinetic energy is conserved, and that's because the elastic object is able to store that energy in itself and then release it again. Mentioned briefly earlier when someone pointed out that elastic is a form of energy. But inelastic objects can't do that. The deflated soccer ball can't do that. And I'm throwing this at the wall. It shouldn't bounce away, but again, throwing this at the wall. That doesn't go back to normal like the inflated ball does. And for that reason, rather than storing the kinetic energy and using it again later, it just turns into something else. Usually heat and sound are the two forms that happen in an inelastic collision. But in that type of collision, the kinetic energy, most of it will turn into a different form, and we consider it to be not conserved. So kinetic energy is conserved elastically, but not conserved inelastically. And that is arguably the biggest difference between the two for the sake of this course. Momentum is always conserved. It has no other choice. But kinetic energy is only conserved in an elastic collision. Which again, I'm not going to do it again, but when you throw this at the wall, it bounces away at a higher speed, kind of evidencing that it had more of its energy left over to be able to do that. So that's why elastic collisions tend to be very chaotic. And you'll be proving that in lab this week when you, I lost my words for a second there. We have an air track, basically like an air hockey table, and you're going to be slamming things into each other to see what happens. Sound cool? Any questions or objections? All right. And in that case, we got just enough time for one more quick thing today. I want to talk about a second form of energy so that on Wednesday we can talk about how energy forms transform from one to the other. So that second form of energy that we'll focus on for the bulk of the course is gravitational potential energy. This is a form of potential energy, to go back to the vocab word from later. So gravitational potential energy is energy that is being stored for later. Any form of potential, it's not being used, it's being stored like a battery. What makes GPE weird, in just given how my students have reacted to it in the past, GPE is not energy stored in chemical bonds, it's not energy stored in an electrical battery. It is energy stored in an object's ability to fall. If you can fall, not falling yet, but if you can fall, you have energy stored up inside of you that is released when you fall. Now, conceptually, does that sound weird? It's okay if it does, I'm just curious. Okay, no objections. Now, as proof that there is energy stored in something's ability to fall, note, if I hold this item up here, it's able to fall about 2 meters to the floor. If I let go of it, what does it start doing? It starts falling. And if it's falling, it must have a velocity, right? If it has a velocity, if this mass has a velocity, what must it have? Energy, specifically in the what form? If it is moving. Kinetic. So before I release it, it doesn't have any kinetic energy. Once I release it, it suddenly has kinetic energy. That kinetic energy does not just spring magically into existence. One of the main points of this week is that energy is not created or destroyed. It has to come from somewhere. So the kinetic energy of the ball, once it's falling, is the transformed version of the GPE it had before it fell. It's got energy stored in it right now like a battery that turns into KE on the way down. I'm going to tab slides real quick just to get to a different picture. As further evidence that there is energy in the ability to fall, we literally power society on some of it, because a water wheel, at least one built like this, the water up here has GPE, so it has energy up here, and we turn that into electricity by allowing it to fall onto a wheel, turning it into KE and making the wheel spin. So literally, this water, by virtue of being elevated, has energy, and that can be turned into usable electricity. So, energy stored in the ability to fall. Sound all right so far, at least? Okay. Tabbing back. Since this is its own form of energy, it has its own formula. Formula for this one, GPE equals mgh. M is the object's mass in kilograms, same as the KE formula. G is the variable shorthand for acceleration of gravity. It's that same 10 meters per second squared number that we've been using. So the G in this formula is 10. And lastly, H, height above the ground, the distance you could be falling. To kind of translate what this formula means into words, the higher something is above the ground, the more energy it has stored and the more energy it will release once it falls. Which again, you've noticed before. If you jump off of, this table, it doesn't release a lot of energy when you hit the floor, but if something falls off the roof, it, by being higher up, has more energy stored and releases more of it on impact. And that's one reason why meteors make craters. They have a lot of energy on the way down. And when that energy goes into the Earth dents itself. So, higher up you are, the more energy you have. Also, the more mass something has at the same height, the more energy it has stored up. If I drop a golf ball off the roof, it won't do anything to the pavement. But if I drop an anvil off the roof, more energy hitting the ground, more likely to crack the pavement. Formula feel okay? All right, in that case, last little bit of practice for the day. Same basic scenario as before, except now the bowling ball is 10 meters off the ground and the person is 10 centimeters off the ground. So, bowling ball on a 3-story roof, person walked up 1 step in a flight of stairs. Which of the two has more GPE, please? Bless you. Yes.
So object B.
B. Any other votes? A. Alright. Object B, mass of, well, scenario B. Technically I've been using that as the mass of a human. So 100 kilograms times G. G is always going to be 10 on planet Earth. And then the height. I listed 10 centimeters. How many meters is that? 0.1. Very good. So this person has a GPE level of 100 right now. That again would be about this high up. So that much energy being released. As for the 5,000 gram object, again, I'm treating that as about the mass of a bowling ball. We like kilograms. How many kilograms is that? 5. So 5 times 10 times 10 actually ends up being 500. This would again be similar to dropping a bowling ball off of a 3-story building, which is more likely to crack the pavement than me hopping off that stool. Now, just contextually, this one does not have a square in it, so the 2 terms are kind of equal importance. Double one term and double the answer. So there's not like that weird catch of the velocity being more important than the mass in the other formula. They're even for this one. And with those 2 forms of energy discussed, as the week goes on, we will look at how energy transforms, how it's conserved, and how we use it. If you have any questions or need anything, do attend lab as normal this week, and please have a wonderful day. Thank you. Welcome. 126, last room on the right if you're heading that way.
Yo, who was that?
So that test will be in here?
Correct.
In my room?
Yeah, there's just more room